She from one of the countries?
My name, I guess. So.
Yeah, no, yeah. I got you.
All right, we have one more minute, and then Dilhan will start off the meeting with a few announcements. Can everyone, if you cannot hear us, shoot me a message. I am at the API WebEx, so just shoot visit us. Also, Linda started this weekend. You should have seen in the CREDC letter. So welcome, Linda. It's the first meeting.
Start off?
Yes.
So, thank everybody for joining, and again, welcome Linda to the team. So, first, you will start seeing notes and reminders from Linda. So, Linda will share your new host. Just a brief, the industry workshop we had, I guess, a week ago. Every single person that I spoke to, very complimentary of the industry workshop. Well done, everybody. The posters, very much. They were really well received by industry. What Linda is doing while we are talking here is actually trying to capture the connections, those posters, to put it on a spreadsheet and for you folks, I know Al, you've already started even before that. If folks, you already have those kind of information, don't for the sheet to come through, please go ahead and get on with that. So we have seen a slight trend downwards on the workshop attendance. Until this year, we've managed to actually turn it around this year. We had about between 140 and 50 people, and based on the stats, what's really good is that it's a 55-45 sort of split between academia and industry, which was a success, I think, and most of them were very, they thought that the workshop and the way we handled it and all the great stuff that was showcased by our students, very well received. I was at EPRI, Electrical Research Institute annual workshop earlier this week, and there were a few people who were at our industry workshop there, and they spoke very highly of the work that you folks are doing, and expect them to be sort of involved with you. And if you send an email to them, and if they do not respond, just that because they are busy, give it a little bit of time, send a reminder. If not, just let me know. I'll try to make connections happen as well. That's all I have in terms of the updates. Our presenter today is Venkatesh from Washington State. Unfortunately, both his supervisors are busy with some other meetings, so they asked me to sort of introduce him. So Venkatesh is on his final year of the PhD. His main research interests are in cyber-physical resilient design and operation of microgrids and distribution systems. So with that, I'll hand it over to Venkat.
Good morning or good afternoon for many people here. And thank you so much for the kind introduction. My name is Venkatesh, as you can see in the slides. The topic that I'm going to be talking about today is about cyber-physical resiliency experimentation using the Federated Testbed. I'm going to be talking more on the federation of the Testbed, and I'll touch briefly on implementation that we've already done and what we plan to do in the future and our vision for use of Federated Testbed. You can see in the slide here that there is a huge team that was still working on this project. So many probably in the CREDC community probably know me. I've been around for 3 years now, but we have new people, and we had some visiting scholars work on this project, and most of you also know Tim and Jeremy from the University of Illinois. So moving on. So the first thing, whenever someone says experimentation with a testbed, is the question as to why have actually testbed. So the figures on your right provide. Sorry.
We're seeing presenter mode. Can you go into full screen mode? Might be easier to read.
Okay. So you're seeing the presenter mode and not the full screen.
Yeah, I think your presenter mode screen.
Okay. Let me push it around and see. Okay. I'm gonna stop sharing for just a second and try to figure this out. Excuse me. Sorry for the interruption, folks. Just give me one more second.
WebEx is not cooperative enough to see their notes and
Presenting. Okay.
So we have to endure.
It's hard to read.
It is.
Okay, let's see.
It's raining. I see a lot of people online.
Okay. Let's share it again. Okay. So goes better. Oh. Yeah, for some reason I think it's just
display settings on top. Hey, Venkatesh, just try and scroll up to display settings. It might be.
At the very top of your screen.
Okay. Is that better? Are you able to see the full screen view now?
Perfect. Yes. Thank you.
Sorry for that hitch, but
Can you get to, can you make this screen?
so should I go when you're able to see the full screen, right? Yeah. Perfect. Thank you. So the question that most people ask is, why do you need a testbed, and why not just go ahead and implement it out in the field where you can actually see what's going on, right? And so I think the pictures on your right provide a better answer than the word describe it. So you have substations blowing up, transformers blowing up, and these things do not come cheap. Most of them are a mix of all pieces of equipment. So we have to test out our power system algorithms and smart grid algorithms in a test bed, which can emulate or be as close as possible to the actual field. And we also need to analyze the cyber-physical interdependencies, and test these as provided in the figure is not a suitable approach. So that is why we need a test bed. And again, why do we need a real-time co-simulation test bed? So the power system right now is becoming more and more tightly intercoupled with the cyber system, as evidenced by our group's name, right? And also, when you have a co-simulation of the communication systems, we also have to consider the control systems, the controls that overarch and control both the physical and the communication systems. And we need to determine if the time-sensitive applications or that work on the power grid can actually perform in that required time. So that is why the real-time concept comes into play, because we need to ensure if the algorithms that we are developing for the control of the power grid can actually work in the suitable time and perform the necessary control actions. So these are some of the challenges that exist in creating such a cyber-physical coastal testbed. And note that we are not talking about federation now. This is just for cyber-physical testbeds. Most of the simulators talk in different languages, so they have their own customary protocols that they use. They have a different way of solving the network solutions or the system of equations that exist. And also, we have to coordinate in operation in real time between all of these real simulators. And the simulator also needs to be flexible enough and not a very niche or a unique simulator that can only work for a specific set of applications. Hopefully, it can also support, say, a plug-and-play architecture where each domain has its own simulator that can be easily coupled with the other sort of simulations that we're already doing. It should include, as I say, building on the previous point, it should include all the different layers, the power system, the communication, the control system, and any other that we might want to do, say, mechanical simulation or something with governance simulations and all that. So it must ensure, it must also allow us to do end-to-end testing and hopefully also close the feedback loop because we want to ensure, we want to study the performance of control algorithms and seeing how the physical and the communication system would reflect on those control actions. And finally, we also need to have the ability to model cybersecurity. And so which is one of the key focuses in the test bed. So now we move on to the next question as to why to have a federated test bed. So the large-scale multi-domain experiments for the power grids and for most systems, they are becoming huge. Like once you start controlling, once you start interfacing all of these different simulations, the scale of the experiments become large. So we need to have a large-scale multi-domain experiment that are required for designing and assessing the resiliency. And also, when we try to interface more and more specialized hardware equipment, for example, in the power grid, we have different reads from different vendors such as LEL, AD, or Siemens. And most universities or most institutions would not be expected to have all of the different controllers and own areas of expertise. And when the experiment necessitates the use of various controllers and various devices and also various power hardware, such as interfacing with PV generators or inverters or small-scale microgrid or distribution system testbed that exists in various national labs, the federation aspect becomes more important and to avoid duplication of effort between different institutions. And again, that the duplication will become cost prohibitive, and it also reduces modularity and flexibility. And finally, when we implement federation, it allows us to actually share resource and intellectual property without violating confidentiality, because we can restrict the amount of data that passes between the various federating institutions. While this would ensure that the algorithms or the tools are tested in a realistic environment, it would also protect the institution's privacy and data that it shares with other people. So these are some of the motivations that we thought were required for the federation of test beds. So the objective of this activity is to identify experiments that can actually benefit from federation and evaluating the experimental needs to balance various things like scalability, the fidelity of the simulation, the complexity and the cost, and developing the interfaces and the management architecture that allows for the federation simulation, and finally to validate and quantify the results that that are from the that we get from the federated experimentation. So here's a very quick overview of the test beds that exist at Washington State and the University of Illinois. These are very non-complete sketches, so if you have more questions about the exact resources at the different institutions, please feel free to chat. So the upper figure that you see on your top left is kind of a distribution or a microgrid test bed. We are in the process of, it already exists, but we are also continuously working on it to make it better every day. And we have different real-time simulators, including RTDS and OpenRT. We have experimented with various different communication simulation architectures, such as Core or MiniNet, and also we've done some experiments with NS3 and so on. And we have database control algorithms and control tools about which I'll be talking about in the later slides. And we've put together different interfaces to connect all these things together. Also, we've performed several cyber-physical experiments on these test beds. And again, for Illinois, it's the same. They have even more devices. They have a bigger RTDS rack, and you have a pretty comprehensive of the various devices and resources that they have over at Illinois. So that's the various test beds that exist at Washington State and University of Illinois. So again, some of the challenges that exist with the geographically distributed simulation. So previously, as cited there, we had a linear prediction algorithm we used to kind of do the geographically distributed real-time simulations. The linear prediction algorithm works somewhat similar to, for the power folks. A good analogy would be, say, the contingency analysis, where you have a predictor and a corrector step. So the linear prediction algorithm works on a similar thing, on a similar principle, where the next time step is kind of predicted in linear prediction, and then the data from the distributed or from the remote site is received, then the corrector is applied. So that is one method that we used to actually address the simulation fidelity issues. But the focus of this talk is going to be more about the VILAS framework. So the VILAS actually is a framework proposed or developed by RWTH Aachen in Germany, and the VILAS actually stands for Virtually Interconnected Laboratories for Large System Simulation. So that is what the VILAS framework actually stands for, and it is basically an interface for exchanging data across these different real-time simulators. The objective again here is to kind of minimize the communication overhead and the latency. Since we are talking about geographically distributed simulations, there is going to be some latency that cannot be avoided, and the challenge then becomes is to how to manage this latency. And again, the numerical stability of the solution itself is another concern, because if some portion of the data is not received on time, especially when doing EMTP kind of simulation or even more slow dynamic simulations, it is essential that the stability of the problem is always considered. And by stability, I mean the numerical stability, which is the convergence criterion for the network solution for the simulation. So here is a very quick description of the VILAS framework. And again, as I said, this is an architecture that was developed at RWTH Aachen in Germany, and initially they had an interface with the Polo University in Turin, Italy, and so basically they previously interfaced OpenRT that was present in Italy and RTDS that was at Aachen, and it works based on a client interface basically, and it passes the data over using UDP packets across the internet, across an unsecured internet, and then the main data exchange is performed at a data broker, which is basically the VILAS framework, and both of those local solutions would only exchange that data that is essential for co-simulating the different that particular experiment. So that would probably become more clear as we go on with the presentation. And so as you can see in the next slide, this is the very simple boiled down version of the VILAS node setup is that you have one laboratory 1 and laboratory 2, and you have the real-time simulators there, and the VILAS node is kind of the interface or the gateway through which the data exchange between those two laboratories take place, and the simulation fidelities or the synchronization between the different simulations is ensured using a GPS synchronized clock. The data packet that's shown below is basically the UDP packet that's sent across bypass node. So data is just the exact data that is required, that is chosen by the operator to change between these two laboratories. Moving on to the test systems that we have used in this work is we have chosen the 179 bus VEC model for the transmission system, and this has been developed on the OpenRT using the HyperSim modeling interface. I've also chosen the IEEE 13 node feeder for the RTDS. And the IEEE 13 node feeder is connected to bus 106 of the VEC distribution system. And we've also developed another test system that we're planning to use in the future, which is a modified 33 node test system, which will be used to demonstrate the federated resiliency use case. More details, of course, are in the slides after this. So as you can see, in the 179 bus system, we've identified the bus 106 as point of interconnection as to where we need to connect the distribution system load. This is because that bus is uniquely suited in terms of the loading conditions, and we've replaced the load that's present in on the transmission system using the IEEE 13 node test feeder. So that's the overall interface one, and I need to emphasize this is still all done locally. This is all at Washington State 179 bus system, and with the OpenRT and the 13 node distribution system is simulated in the RTDS. This is basically how it works. The first laboratory, so this is still in the same laboratory, but for the purpose of communication, we use laboratory 1 and 2. So we have the OpenRT and HyperSim, and then that has a shared memory with the Villas node, with the real-time Linux server that exists in the Villas node, and that takes in the data. In this case, it provides the voltage information for bus 106, and it takes in information from the distribution system, including the loading conditions and the current. That is shown in the next slide, which is that the voltage and angle data is provided to the distribution feeder model. So that is interfaced at bus 650, which is considered to be the substation node, and the P and Q information and the current information is sent back to the transmission system. So that is the data exchange that is happening in this core simulation. We've also tried to compute the latency that exists when using the Villas node and interfacing these two devices or these two simulators. So the round trip time is the critical piece of the puzzle, and this allows us to constrain the different types of problems that can be studied using the federated testbed. And also, these are the various different components contributing to the round trip latency. And we've kind of zeroed in on an ideal packet rate that or the maximum packet rate that we can use for these sort of simulation, and that is anywhere between 1,000 to 2,000 packets per second. So this is the graph that shows the resilient response of the transmission system on removal of the distribution system. So that's the graph on your left, which is basically showing you in the 179 bus system what happens if you disconnect the IEEE 13 node feeder. So you can see that there is clearly there is an effect on the transmission system. The loads are both going towards zero, and also the feeder voltage is also going towards zero. So, and you can see that there is not much of a time difference that exists, or there's not too much latency that exists. So I think it's basically just one cycle, 16.67 milliseconds that exists, being the effect of, or the effect of the distribution system feeder being disconnected from the transmission system. Also, the round trip time is observed to be 0.0035 seconds. That was observed in the other side, on the client side, in the RTDS side. So that is basically the whole experimentation part that we've done. We did using the Villas node framework, which is to say we have connected the OpenRT and the RTDS, and we've simulated, co-simulated, I should say, the transmission and the distribution systems. And we've observed the latency and the effects of one system on the other, and we've also kind of zeroed in on a packet or a bandwidth that can exist between the federation use case. talking about the federated testbed, the question that most people have is, what's the use case for federation, or why should I put my resources so other people can use it, right? Like, what are the different use cases or simulations that can be performed, or that can be performed easier using federation? And so to address that question, we have taken or studied different use cases. As I mentioned before, the slow-moving dynamics is one of the phenomena that can be studied using federation. And so we were looking into ideas for federation that can enable data sharing between different resiliency tools and or federation to enable resiliency assessment. So it's going to be the next little focus of my talk. Federation is actually is kind of required for bigger use cases because consider the sizes of the systems, and also if you consider the holistic co-creation that is required to understand resiliency, federation has tools that make it easier. So in our very specific case, the RTDS at WSU has only one rack, and so that is one of the reasons why we chose IEEE 13-node feeder, because that is the limit of the size of simulation that can be performed at WSU using one rack of RTDS. But as you can see, well, we cannot see it now, but 13-node feeder, as you can see on the bottom right of this slide, there exist only two switches in the whole system, only one voltage controller or voltage regulator that exists in the whole IEEE 13-node system. So there's not a lot of scope to demonstrate resiliency and to demonstrate a lot of different use cases that exist in the actual field. So that we chose to move on to IEEE 33 bus system, which is to actually demonstrate the various use cases and changing resiliency. So I'll be showing you the system and the various cases that we did later. And also the transmission system will be using the 179 bus system, the Opal RT. So again, that's a bigger system than most real-time systems can handle. So if, for example, if one university maybe or one institution has maybe just 4 cores of processing in the Opal RT and another has 12 cores, there is an opportunity to collaborate and exchange data between those two universities or two institutions and connect those two systems together and then start simulations that way or perform experiments that way. And in our case, for right now at least, the Federation, the communication systems are actually simulated locally, and any data between the communication systems is not exchanged right now, but the node framework is flexible enough to actually accept data from multiple simulators and send the data over the internet to the other side on the remote side. So in future we will be also using the Velas node framework to actually interface the communication systems together. And right now the communication systems are just simulated locally, so we are studying the performance or the effect of cyber attacks on, say, the distribution system on the transmission system. The transmission system would not actually know that this is the result of a cyber attack, but it would actually see the physical impact of the cyber attack on the transmission side. As I said, on the level, the data from both systems are fed resiliency tools, locally also exchange information. As I said before, the modified 33 bus system is used here, and we have looked at different cases such as the attackers get access to the cyber network and then opening the circuit breakers, and also looked at various other cases such as loss of transmission lines that disrupts the power supply, resulting in net reconfiguration as our control strategy. So this is the modified 33 bus system. I say modified because added a couple of lines and also added some generators, some distributed generation in the system to enable to demonstrate resiliency. So we've very specifically studied 4 use cases. The first case is to have the grid disconnected, the main grid disconnected. And the other 3 cases are the various generators exist in the system, and all of these generators or nodes being compromised. So this is the modified 33 bus system, and this is what we are demonstrating for the physical resiliency of this system and the effect of this system on the transmission distribution system. So a very quick detour into the physical resiliency metric that we are using. So the resiliency metric that we are using is more of a real-time operational metric, and it does not look at, say, any historical values or any post-event analysis. So it's more of a real-time metric that is taking in various different inputs from the topological factors and also elements that are available from the simulation at that point of time. So looking at various topology factors, including clustering coefficient, SMU metric, the source redundancy, and also some operational factors such as loss of load and the number of generators available, and also the probability of availability for each generation, and the number of switching operations that is required to kind of move from one configuration to the other configuration. So the parameters that exist on the left is normalized between 0 and 1, and the base case is assumed to be the most resilient system, and that is the configuration in the steady state. And then weights are assigned to each of those factors on your left using pairwise comparison, but it can also be assigned based on operator intuition or as per the system operator's requirement. And once weights are assigned to all of these factors, they are combined using a process called analytical hierarchical process, which decision-making process to combine these factors into a single resiliency value. So please do let us know if you have any more questions. We have already some work published on this area, but so that is the kind of physical resiliency metric that we are using, and that is the work that we'll be demonstrating using the federated testbed. Again, just show you a small graphic about the AHP. So the way the AHP works is on your left you have a small sort of vertical line that shows you the different components that goes into it. So you have various options. It's basically the various feasible reconfiguration states for the distribution system, and your main criteria and the sub-criteria that affect your cyber-physical resiliency score. So your main criteria would basically be topological factors, physical factors, and some cyber factors. And the sub-criteria can be classified or can be understood as terms that contribute to each of the main criteria. And finally, these are combined to provide you one single goal, which in this case is the cyber-physical resiliency score that is calculated in real time for different operating conditions. So that is a basic overview of how the AHP works. And so these are the results that we have for the physical resiliency for IEEE 33-node test feeder. So as you can see in the steady state, that has the highest resiliency, which is somewhere around 9.1, I believe. And so you have the cyber physical resiliency for each of those different cases. And for the case of the main grid, which obviously has the highest impact, is the microgrid or the distribution system is reconfigured, so each feeder is supplied by its own distributed generation. And you also have different cases where you have the bus 13 being disconnected, and the bus 24 and bus 30. But in all of these cases, the main grid can supply the load is being supplied by the distributed generation. So the on the resiliency is not that significant, but the overall process shows you that for various different conditions, the resiliency can be assessed in real time and can be computed using the process that was just mentioned. We actually propose to federate the resiliency use case, because right now the part that I presented is just for the IEEE 33-node system, and in future we have to interface that with the transmission system to study the effect of resiliency of the distribution system on the transmission system, and also vice versa, in which case to study the effect of dynamics of the transmission system, the distribution system. This is a very quick graphic or a plan that we are going to use to federate the resiliency use case. One is to have the OPLRT simulating the transmission system, and we will have the transmission system resiliency tool, the kind of interface with the OPLRT and its associated communication architecture, and we will be exchanging data with the VILAS node, which will be voltage and the transmission system resiliency, which is being sent to the distribution system side. And for the distribution system, we'll be using the IEEE 33-node test feeder, and the IEEE 33 node test feeder cannot be actually simulated at the WSU facility. So we'll be using the facility at Illinois to simulate the IEEE node test feeder. We'll again be having a Villas node that is present at the remote location, and we'll be exchanging data including the current and the loading phenomena, and also the transmission system resiliency will be used for the distribution systems resiliency formulation, and distribution system resiliency score will be again sent back to the transmission system. So that's a very quick overview of the summation or the overall Federation resiliency experiment. And so this is kind of our overall vision, or the grand goal that we're trying to achieve by using Federation. So in order to perform holistic and realistic resiliency assessments, we need to consider all the different systems that contribute towards resiliency. So that means the transmission systems, the multiple distribution systems that are connected to the various points in the transmission system, and the various multiple microgrids that might be present in each feeder of the distribution system. So that, in effect, itself is a vertical simulation of, or hierarchical simulation going from the transmission down to the microgrid level, and the data is exchanged between all of those using the Villas node, and by rating the various systems that needs to be simulated across different institutions. And for now, we plan to have the communication as more of a local simulation that is connected to the real-time simulators at each local location. So we'll be having, say, NS3 that is connected to the OpenRT or for the transmission system, and we can have MiniNet, and we can have, say, core for the different distribution and the microgrid simulations. And again, these data can also be exchanged over the Villas node platform. And finally, we also have the energy management system is showing you the overall visualization for the transmission system, and similarly we have the DMS and the microgrid management systems that shows you or allows you to perform control actions on each of those local relations, and the effect would be reflected by exchanging the data across these different sections. And finally, we also have local resiliency assessment tools that we're also developing, and we have a transmission system resiliency tool which is still in development and which has a physical resiliency assessment similar to the one that I've proposed above. And we also have a distribution system resiliency tool called PyVis that is already out there, that is ready for use, and that again works off of similar concepts. We also have a microgrid system resiliency tool, IFER and CPSAM, that can also be used towards assessing the resiliency or quantifying the resiliency for the microgrids. And we plan to interface all of the different tools together and creating a holistic system resiliency score that can be used by the operator. And finally, let's not forget the little guy waiting just below the microgrid system. That's the cyber attacker, and he has access to all of the different systems, and we can perform or can do proxy cyber attacks on the physical systems. We can do injection attacks on the location models, and we can do again compromises and vulnerability exploits on the different controllers on the controlling platforms that exist in the whole system architecture. So this gives us a way to understand the interactions that might not be obvious otherwise. Like, what is the effect of the microgrid management system being compromised on the distribution system on a specific feeder, and also maybe if there is an effect on the transmission system, what is that kind of filtered down to the distribution and the microgrid model. So that's kind of the overall goal or vision that we have for this project, and we've already have put pieces together, and we'll be working towards completing and executing that vision in phases. So here's some things that we kind of learned when we used the Villas framework. So the framework actually provides a way to nicely abstract the complexities involved in federating different test beds. And Washington State has also contributed to the Villas framework by developing the code for interfacing with HyperSim. So previously, the Villas framework had input for RT Lab, which is another modeling interface for OpenRT. But we've kind of also developed an interface for HyperSim, and which we've uploaded. So the VLS framework is open source, so we've contributed to that repository. And the developed Federation approach is actually very useful to test the performance of the algorithms in real time. So we also have other tools such as voltage stability monitoring tool that we've developed at Washington State. And the Federation environment actually allows us to test the such tools on a holistic simulation in which we can observe the effects on the distribution and the microgrids or proposed algorithms. And again, as I said, the interfacing of various resiliency tools is kind of the aim that we're going towards. And another key point of Federation, which I like to emphasize, is that the Federation allows you to actually test the various algorithms with actual hardware. So the reconfiguration can be implemented, say, in a substation controller, or to be more specific, say something like an SEL real-time automation controller, and we can study the performance of the control algorithms in real time with the Federation, and also study the interaction between different systems. What are the challenges in Federation? So one of the main things is to validate the accuracy of the simulation, and this goes back to the numerical stability problem, and also study the different results from the local simulations, and understanding and how the performance is affected due to the latency. And exchanging more and more data will come with increased latency, so it would be restricted in terms of the use cases that we can possibly simulate with Federation. And simulating a single system across different simulators. For example, say, spread the 179 bus system across two different simulation platforms will be more challenging, because that system is more likely coupled than, say, doing transmission and distribution at two remote locations. We also need more experiments to study the performance of the controller hardware in the loop and the power hardware in the loop simulations, and understanding if the remote location is controlling a specific piece of hardware in the client location. So how does the latency affect the performance of the controllers and the power hardware in that case? So experiments are needed to study the performance in scenarios. And also the communication latency kind of restricts us into not studying faster dynamics, so we cannot probably do say fault analysis or transient simulation or any EMTP kind of simulation at point. But it might also be possible if we develop better kind of prediction algorithms or faster interfaces that allows us to reduce the latency or manage the latency in a better way. And again, one of the other things is that interfacing with different facilities or different institutions provides significant logistical and operational challenges, especially if you have to, say, encrypt or use some sort of protection a VN at each of the client locations. Coordinating again with different institutions would be a challenge. And we are looking at more use cases and studies and experiments that can be performed on the federated testbed. As I said, the cyber-physical resiliency tools, the metrics that we have for the transmission, distribution, and the microgrid, all of those will be interfaced and will be tested and validated using the federated testbed. And we are considering more hardware in the loop simulation that will consist of, say, PMUs, relays, and controllers, any other power hardware that our client or our federating institution would be interested to use. And we will also be studying more formally the effect of latency and how those can be mitigated for federation. We are looking at more collaborators that bring their own set of expertise into the federation experiments, and we can interface those different simulators and different devices too. And I guess that's all I have. Thank you.
Thank you for that presentation. Do we have any questions from anyone on the call? Sorry.
So I have a question. Just out of curiosity, the underlying framework, does it pull any ideas from the HLA kind of framework? which is IEEE 1516.
Right. I believe the Villas framework is not exactly inspired by the IEEE HLA. So this is more of an asynchronous, and I mean the IEEE HLA also proposes standards for, I guess, correct me if I'm wrong, but it proposes some frameworks for actually coordinating the time between the various simulations, but the framework actually does not have a lot of care for the timing aspect. It allows the local institutions to use GPS clocks to synchronize those local simulations. Our focus is more on the data exchange or the data brokerage part of the distribution simulations.
Add into that answer, I believe HLA requires, some access into the system model. If you have a proprietary model like RGDS and polarity, HLA is not a solution. We did explore it, part of the research, not a part of the CREDC, but another project, and it was not very successful to interface in real time with no control over simulation. But with this Villas node, the thing is that it's more about interfacing issues. So once you create it relates to that. So in a way, we have looked at both, and but I'm not expert in HLA, so maybe it might change also since we 10 years before.
The interesting thing about HLA is they try to solve the timing problem, but the data communication problem is then left undefined. Communication, but it leaves the timing.
Tools are kind of working different difference of the problem. So maybe there is this hope for synergy somewhere. So.
Okay. I don't have any other questions coming in at this point. Thank you, Venkat, for your presentation today. If we have any other questions, just to let you know that we'll have the recording and the slides sent out than the last time. So I mean, I'm better quality than I did last time. So everybody, and we do have a meeting next week, I believe.
And just to add a final note, we're looking for more collaborators on the Federated experiment. So if you're interested in sharing any resources, or even if you're just interested in asking more questions, please do feel free to reach out, and be happy to collaborate with you. Thank you.
Thank you. And we'll have a presentation next week for September 28th will be on risk models. So
Before we hang up, Venkat, got a question for you. So if you're looking for some more collaborators, I guess it's a question for me as well. Have to be an institution within the CREDC family, or can it be outside of that?
Yeah, I think for industry, outside is okay, but for institution, we'll prefer within CREDC.
Well, okay, the only reason I asked is I was having a chat with the University of Arkansas under the SEED program, and they have a test bed, and they were sort of interested in working on the Federation as well.
Is that, still at what other...
I can forward you the contact information from Arkansas, and you can have this thing.
thank you, everyone, and we'll talk to everyone next week.